So hello and welcome students. Let's start our course MA412 linear algebra. Okay, and this was the lecture number 2. Lecture number 2. Okay. So now recall that in our last lecture we have defined something called linear space or vector space. So this kind of a order tuple. So you have a non-empty set and a field and two operations, quadruples, yeah, and they satisfy certain conditions, right? And then we define something called subspaces. So this was defined already, linear space. What if? And then subspace, which is itself is a vector space and subset of W. Okay, and then there are lots of examples. For example, a singleton 0 is always subspace of V, and V itself is subspace of V, right? And there are many examples I have given in particular vector spaces, right? So today we learn many important idea, but for that let us just try to check a property. So this is very simple property. So if you have a subspace W, so let W be a subspace of V, okay, and so you choose some finally many elements inside W and say small w1, small w2, some finally many element W, then for any constant, in many constant, say C1, C2, Cn belongs to F, the sums C1 W1 plus C2 W2, and then you add up till this Cn Wn. So this will be always inside W. Okay, this is true for any number of finite number element of W, any constant in F. Okay, this is true. And the proof is simple. You just use the mathematical induction. I hope everybody is known mathematical induction. So I am assuming that okay. So let me just let me just write down what is my assumption. My assumption is ZFC, and this is the ZFC means germinal functional choice. With the choice is axiom of choice, with axiom of choice. Okay, and it is known that this axiom of choice is equivalent to mathematical inductions and many other equivalent forms. So mathematical induction I am also assuming, and I am assuming that you guys already know it. Okay, so now this is just you do it as a homework. Use mathematical induction to prove this. Okay, so this is kind of homework. This proposition use mathematical induction. Mathematical induction. Okay, so you can easily prove it. So for example, when n equal to 1, this is obvious. This is definition of subspace, right? It's constant time W, and For 2 is also obvious. Now if we assume for n, then we need to assume for n plus 1. So if we assume for n, say suppose there are n many elements, vectors w1, w2, wn, and constants c1 should cn, such that the sum is inside w. So you can say write down this is an element, say x, and then if we add one more element, say wn plus 1 with a constant, so again it will be of that form only, right? So so that is by definition of again vector subspace. You can find out that. Okay, so this proof is simple by mathematical induction. Now this is just some property I will use somewhere in future, so I am just telling you. Okay, now these kind of sums has a nice name. They are called linear combinations. Okay, so let me define it thoroughly. What do you mean by linear combination? So linear combination. So you have a vector space and some subset. So let me write down, let you have some subset, say S, B A belongs to V, A subset of V, B A subset. So I did not say that is subspace. Okay, subset of. So in the last theorem, this was subspace, but here I am just telling subset of V. Okay, so we say a vector or an element, whatever you write down, an element, say x belongs to V, is said to be a linear combination of vectors from S, if there exists finally many vectors, say some v1, v2, something, say vm belongs to S, and some constant, say c1, c2, cm belongs to that field F, such that what happens is that your x can be written as sum of this. So it can be written as summation ci vi of this form, where I is starting from 1 to m. Okay, then you say that x is a linear combination of vectors from S, and in particular you can say that S is a linear combination of this vector only, v1, v2, vm. Okay, this is the definition of linear combination. Now now maybe I can give some example. So so you start with so let me start with R3. Okay, so R3 is my vector space. In real life we know that there are like R3, right? So there is something called dimension that I'm going to define it next soon. So here if you take a point in space, so you can have say 1, 5, something 3, and then the issue that these vectors. So what does that mean? That means it's kind of a vector. You go 1 unit and then you go 5 unit and then go 3 units. You can find out something like that. Okay, so 1 unit, okay, then 2 unit, 3 unit, something like that. Okay. So issue that this kind of vector, you can write down this linear combination in different way in different vectors. So let me write down in one way. So I can write down this linear combination, this 1 times this vector. So this is one vector in R3 of this form 1, 0, 0, and then we have 5, and then 0, 1, 0, and then you have 3, 0, 0, 1 of this form. Okay. Obviously, there may be different other vectors which you can write down, which you write down in a combination as a this vector also. This is possible. Okay, always. So this is there's an example that you can write down. So this is an example that this is in a combination of these, and these three vectors. Okay. Now, coming back to the question I was about to ask you, that what happens if you collect all such linear combinations of some set, and that is called something called span of that set. So definition again. So so S is a subset of V. So we say, so now we say, so the span of S, so is the, what is that? Is collection of all linear combinations among the elements. What does it means? So you can say that this is linear combination of all the vectors in S. So we can write down collection of all linear combination of vectors, which are also sometimes we call elements also vectors. Yes, okay. So inside S, whatever the element are there, you take linear combination. So those linear combination will be inside V, right? So if you collect all such things, they are called, that set is called the spanning set. Sorry, span obviously. Okay, and we write down the symbol span of S, and also we can write down the symbol that is this kind of bracket. Okay, so this is collection of all such linear combination whose vectors are from S. Okay, is it clear? So again example, maybe the last example will be equal to R3. Okay, and then you choose a set S, which is something like that, 1 1 0 0 0 maybe 0 1 0 1 0. Okay, so if you collect these two things, so this is your set, one set. Now if you take that linear combination of all such vectors, you can see that this will be some copy which is sitting in R3, this proper subspace, which is a copy of R2 actually. So I can write down this is actually, okay, so there's something called isomorphic. So this isomorphic to R2, this is sitting inside R3 actually. So how do you think R2 is in R3? You can take all the triple vectors whose last coordinate is 0, and that will be actually a similar copy of R2. Okay, R2 means in plane, so the vectors are of the form A, comma B, right? Okay, so so this is called the span of a set, and it has a nice property. So what is the important property of this set? So this the span of S is a subspace of V. Moreover, it is the smallest subspace of V containing S. Containing S. So what does that mean? That means if you have any other subspace which contains, that also contains span of S. Okay. So this is very important property, that the span is not any general kind of set. This is actually forms a subspace. Okay. And the proof we require, otherwise we will not accept it. Okay. So what is the proof? So what happens if that collection is itself empty? Okay, so maybe I should say here. So the span, when I define it, I'm also using one notation. Whenever S is empty set, then we say that the span is actually singleton 0. So this is our convenience to avoid some other ambiguity. Okay, so the span of a empty set is always is vector space containing only 0. So if we have an element containing 0, that will be a vector space over any field, right? Over any field. So so that is obvious. Then if S is empty, then span of S equal to singleton 0, right? So this is obvious. Then this is a subspace. Okay, and so done. So in this case, this is done. I mean, you should write down in details. I am not writing all the statement because I want you to understand and write on your own language. Okay, so whenever you have some kind of gap which I am interested in not writing, but I am telling obviously that you need to go at home and you need to write it down properly. Okay, so this is clear. So span of S is singleton 0, and that is also subspace, right? And not only that, this is the smallest subspace, right? So it is inside any other subspace, right? And this contains also phi. Now so if S is non-empty, then what happens? Then obviously in span S you have more than one element. Okay, then you choose so some element, so it doesn't matter. So what does that mean? So that means you can choose any element. So then choose something. Say x belongs to span of or rather I can choose inside S only. I don't need to choose span of S. So this is non-empty, so I can choose one element. This is my x, and whenever I have element x, so I know that the 0 vector I can write down that nothing but linear combination of scalar 0 into x, right? And by definition, this is element of span of S. The span of S contains all the linear combination. Okay. So that is clear that the 0 vector, that this is my left side is vector. So I am not writing the sign vector sign, but this is, you can say that as a vector. Okay. So that is the element of that S, span of S. Okay. So the first condition satisfied, that to prove something is subspace, you must have a 0 element, that is 0 vector. Okay. And now what are the other conditions? That it should be closed under addition and closed under scalar multiplication, right? The condition 2 also you check. So you choose 2 elements. So let x and y belongs to, say, the span of S. So by definition, you can write down x is of the form summation some alpha vi I equal to 1 to n. Okay, and so remember this thing. So these alphas are okay. So let me write them. And y equal to some beta ui, something like that. I equal to maybe 1 to m, may not be same. Okay, n and m maybe are different. So this where this alpha i's, beta i's are actually constant. So these are element of F, and this vi's and ui's are actually element of S, right? That's why I write that this is, that's why x and y is an element of sin S, right? Now when you have this kind of sums, so you can add it. You can add it, and the addition is I already said. How do you add it? So addition will be the addition of full thing, full vectors. So this is full sum alpha vi plus beta ui, right? Because ui and vi is the element of S, so any corresponding combination will be element of span of S. I can say beta j also, ij, so this it doesn't matter, it's a dummy variable. Okay, so this is again, this is element of the span of S. Okay, and similarly it is true for the scalar product. So multiply by this with x, this will be summation c alpha vi, right? I equal to 1 to n. So this is also element of again span of S. So what does that mean? That means this span of S is a subspace, right? That is clear from here. Subspace of V, right? Now we need to prove one more thing. We need to prove that this is the smallest subspace containing S. Okay. So to prove that thing, so let choose another subspace, say W be a subspace of V containing S. S. Okay, so that is what that is. S is sitting inside W. Then I need to prove that. So what is our claim? Our claim is that in this case, span of S is also sitting inside W. Okay. And how to prove this thing? So to prove something is subset of something, what you need to prove? You need to prove that every element of this span of S is an element of W. So you choose element. So let some V, which is summation ci vi I get 1 to n. So ci's are constant and vi's are vectors inside S. Okay. So this is an arbitrary element. So be any arbitrary vectors are element in span of S, and we need to show that this element is also inside W. Okay, so now you see that because S is inside W, so this Vi, now note that these Vi's are element inside W, right? Because Vi's are element of S and S is inside W, so Vi's are also inside W, and W is a subspace. Now you recall that I just proved one property, that if W is subspace, then any such sums will be again an element of W, right? So this property I already proved it. So thus if you take the sums, so V will be summation ci vi, which is the sums of the element of W, so that has to be again inside W. This is again inside W, and I choose arbitrary element, so that implies that the span of S is actually a subset of or subspace of W. Okay. So what does that mean? That means whenever you choose any such subspace which contains S, that also contains subspace which containing S, that also contains the span of S. So span of S is the smallest subspace of V containing S. Okay, so this is the proof. Okay, so now maybe I will give some example here to find out span of something. Okay, I have only given an example before. Okay, so now let me define one something called spanning set of a vector space. Yeah, so a set is subset of V is said to be a spanning set or generating set. We call both spanning set, or we can also call generating set. For V, if something happen, if this span of S is nothing but the full subset, full subspace V. Okay, if span of S is full subspace V, then we call that S is a spanning set of V, or S spans V, or S generates V. We can say also that S we can also say that S generates V, okay, or S is S spans V. Okay? Now again, you recall my example, previous example in the R3. You see, if you take this set 1 0 0 and 0 1 0 and 0 0 1, and you can choose something else also, 1 1 1. So you see that this is also spanning set of V. Okay, maybe the last row still is spanning set, but I just want to show you some example which is not exactly something nice agreement which I am going to teach you. So, okay, later. So you see that this is actually V. Okay, so this is actually one of the spanning set. Okay, and you can do this. You can play this game with a different kind of subspace, as this is a vector space plan, like space of polynomials, space of functions, and find out this homework. Find out what are the spanning set, how it look like. And also the spanning set is not unique. There might be many spanning set. Okay, much more than okay. Okay, so this was that idea of spanning set. Now, the third question is that do you have some kind of some way to understand this spanning set, which is actually characterized the vector space V, like something that before that I need some idea called linear independence, linear dependence, and something called basis of vector space. Okay, so this idea I require. So let me discuss that. Oh. So start with the definition. Okay, so maybe I can define like this. So we start with the set. So a subset of V, some subset of V. We say this is linearly independent. So I'm not assuming S is finite or infinite. It can be anything. Okay. So we say that S is linearly independent and then over the field over if the independent subset, I mean to say that set if So linear independent means what? So if you choose any finite remaining elements, okay, so maybe I should define it for finite remaining element first. Okay, then yeah, so let me define it for finite remaining element. So then we will go for a set. So how to define? So let some v1, v2, vn be n element inside v. Okay, so we say this vi is v1, v2, vn are linearly independent over if what does that mean? That means if any linear combination of those will never be zero. So what does that mean? If for any c1, c2, cn not all zero, okay, obviously for zero it will be not all zero. This linear combination summation ci vi I equal to 1 to n cannot be zero. Okay, obviously if you choose all the c1, c2, cn are zero, then it will be zero. So that's why I'm choosing not all zero. Okay, so what does that mean? So in other words, if summation ci vi I equal to 1 to n equal to 0 for some ci's, then all the ci's must be 0. Then all the ci's must be 0, identically 0 element, 0 scalar. Okay, 0 number. Okay, so linear independent means so you choose any finitely many. I mean, this is for finitely many thing I'm assuming. You choose any such numbers, then if they are not 0, then their linear combination cannot be 0. Or if you start with the linear combination 0, that will force it. Linear independent means that force all the coefficients are must be 0, right? And then you can say that what is linear dependent. So if it is not linearly independent, then you call it linearly dependent. Okay, linearly dependent means it is not linearly independent. Okay, now come to my other definition for a set. What is so this is I define for finite numbers. Now we can define for set. So wherever if every finite if every finite, so this you can kind of thinking as set, right? This you can think as a set. You have Vn. So every finite subset of S is linearly independent. Independent. Okay, if this happens, then we say that S is linearly independent or whatever. Okay, and if S itself is a finite set, then obviously I define the previous one. Okay. So now let me give some examples. So example. So maybe we can choose some other things. So so we maybe that polynomial over real numbers. Okay, space of polynomials over real numbers. Now in this set you see that so I just want to say that something is linearly independent. So you see that you have a set uh, 1, and then that monomial 6, the monomial x square and x cube and so on. Now you see that this set is a linearly independent set, because whenever you choose any final living set one, so this is linearly independent independent. Okay, so okay, so and the proof is also simple. So you choose any linear combination, and that will be linearly independent, because whenever you have summation some ci xi I equal to something can be 0 to something, or you can be some 0 to say m, some say can, if it is 0, identically 0 polynomial, and that will gives you the ci's are all 0, right, for all I. This is true for any combination, any final combination. This is linearly independent subset of this piece of polynomials. Okay. So so one can now ask, one question is that what happened to that empty set? I mean, do you say something about empty set? So empty set is always linearly independent, because linear independent means it must have some element, right? Now, if you have an element set which is a singleton set and non-zero, that also linearly independent, because so example, so empty set, I give one example. In general, empty set is linearly independent in any vector space, linearly independent, okay, in any vector space. And similarly, a set containing singleton points, if you choose something, some points, only one points, and then there has to be linearly independent. Why? Because if it is linearly dependent, as if it is some constant time, then linear combination is 0, that implies x equal to 0, as because c is a constant, right, inside f, so c inverse exists. You multiply by the c inverse, then it will be c inverse times 0, which is 0. Now left hand side is what? C inverse into c into x is equal to 0. But c inverse c is 1 into 1 times x equal to 0. Now you know that property of vector space 1 time any vector is same, right? So that will give you the vector 0. But I already assume that the vector must be non-zero, right? I chose as non-zero, x is non-zero. This is the contradiction. So this is not possible unless c is itself 0. In the moment c is non-zero, then x becomes 0, which is a contradiction. So this forces that. So thus c must be 0. Now suppose that if you know something is linearly independent, some subset, and you have something which is inside that proper subset, then what happens? So maybe this is property, you can check simple property. So so you have some S1 subset of S2 subset of V, such that subset such that what happened, such that S2 is linearly independent subset of V, independent, then that implies then S1 is also linearly independent. Okay, linearly independent over the same field. I am not writing. When I am saying linearly independent, I mean over the field. Okay. And the proof is simple. Why? Because if not, if this one is not linearly independent, then what happened? Then there exists some vector, right? v1, v2, some vn, and this is vector in S1 and some scalar c1, c2, cn. Obviously, in bracket I should say not all 0. They are inside F such that what happened? Such that the summation Ci Vi has to be 0. It will be linearly dependent, right? But the problem is that these Vi's are also element of S2, and S2 is linearly independent. So, and if you choose constant which are not 0, then the summation cannot be 0 inside S2, right? So this is a contradiction, as this is a contradiction as S2 is linearly independent. So I am just short form writing a line, but you should write down full form, linearly independent. Okay. So what is the meaning? So meaning is that whenever you have a bigger set of linearly independent, any smaller subset of that is also linearly independent subset. Okay. And hence the counterpositive is what? Whenever a smaller subset is linearly dependent, then the bigger one is also linearly dependent. Okay. Clear? Obvious. Now the natural question one can ask, if I want to extend the linearly independent set, then how do I extend? Like, how do I extend with another vector? How do I check that is giving you a new? So suppose this is given a linearly independent set, and you want to extend it by say some vector v. Okay, then can you claim whether this is also linearly independent or not? This is a simple question, right? And you have a simple answer to this question theorem that tells you that so let's start with that. Let S subset of V be a linearly independent subset, okay, and V be a vector which is inside V but not inside S V minus S. Okay. So then how do I check that V union V is linearly independent or not? Then this is the condition. Then S union V is, so this is a bigger set, right? It has one more element than that, is linearly independent if and only. So this I double means if and only. This is a both sufficient and a second condition. What happens if and only your that small v, this must be element of linearly dependent, I should say. Also the same. So let me first write down dependent. Then this is if and only, no. So one if and only means that it is linearly dependent for some condition, means if the condition is not true, then it is linearly independent, right? Linearly dependent if and only this v belongs to the span of S, and hence you can say that linearly independent if and only if v does not belongs to the span of S. both are equivalent condition because this is Fernandez, right? So now how do you prove this kind of statement? So again, the proof is simple, not so difficult. So recall that one part is obviously obvious. Oh, oh my God. Yeah. So recall that one part is obvious. If you start with a linearly dependent set, then obviously you can write down. Okay, so let me give the proof properly. So proof. So if this S union V is linearly dependent, then what happens? Then obviously you can have vectors such that this linear combination is 0, right? So obviously see, so S was linearly independent event. So if you choose vector, one must be V, right? So there exists some V and then some U1 into U1 into Vn. Because if you choose only V1 into Vn from S, then it is linearly independent. So the combination cannot be 0 unless that all the constants are 0, right? And 0 and the constant some C0 maybe C1 Cn belongs to F. Okay, not all 0 obviously, not all 0, not all 0, some may be 0 but not all 0, such that what, so we can write down so C0 V, okay, plus summation this CIVI is equal to 1 to n, this is 0, right? And hence see C0 cannot be 0 obviously. Here you can say that C0 cannot be 0 because if C is equal to 0, then this sum will be 0 and that is contradiction. That is a contradiction. Okay, clear. So C0 cannot be 0. So you can write down C0V is minus summation CIVI I equal to 1 to n, and hence C0 not equal to 0 means C0 inverse exists. So we can write V equal to minus C0 inverse summation CIVI I is 1 to n. Okay, so sorry, this is V equal to C0 inverse. Okay, CIVI. So you can write down V in terms of combination of VI, right? So this is new constant. You can write down CI by C0 is new constant. So you can write down this alpha I VI is I equal to 1 to n, right? And hence this is the element of span of S, which I was telling that this is linearly dependent if only inside span of S, right? So one part is obvious. If you linearly dependent, then it belongs to span of S. And conversely, you need to prove that. Conversely, let this V belongs to span of S. So then there exists V1, V2, Vn belongs to S, such that whatever you can write in V in terms of some C1 CIVI I equal to 1 to n for some CI belongs to F, right? Clear? This is okay. So what does that mean? That means you can write down now obviously V is not inside S, So we can write down this is minus 1 times v plus the summation ci vi. I can do 1 to n. This is 0, and see that this minus 1 not equal to 0, right? So you have constant minus 1 c1 cn such that this linear combination is 0, and minus 1 is not equal to 0. So what does that mean? That means so that means the set is union this v is linearly dependent because you have a collection v1 v2 vn and v such that the combination is 0 but the constant are not all 0, right? That is the proof. So if you want to extend the linearly independent set, you need to choose one vector which is not inside the span of that linearly independent set. Then only you can extend that by a linearly independent set, right? Okay. So maybe I will stop here today.